Right, welcome to Work Energy Power, grade 12. Okay, we're going to start considering an object which is lying on a flat horizontal surface which is frictionless, right? And we're going to subject this object to a sideways force. Now from Newton 2, you should remember that if an object experiences a net force in a direction, since this is frictionless, there's no retarding force, that object will accelerate in the direction of that force. In other words, it would experience a displacement in the direction of that force. So this is quite simple. We call the displacement delta x and the force is F. The formula we're going to use to calculate the work is simply the force times the displacement. In this case, we can reduce that to F times delta x. And obviously, if you want to put some numbers in, let's say the force was 20 newtons and the displacement turned out to be 5 meters. Then you could say, all right, the force times delta x would be 20 times by 5, and that would give you 100 joules. Because the units of work is joules, it's exactly the same as the units for energy. Now this situation is pretty simple because everything's moving in the same direction. We have the force and we have the displacement in one direction. Work is force times displacement. You just multiply the two values. But what if it's not in the same direction? So here we're going to assume that the force is applied at an angle to the surface. Now we're also going to assume, I've set up here, that the weight of this object is much bigger than this force applied. And so the object has got no chance of lifting, the force has got no chance of lifting this object at all. But what happens now is the object would still experience a net force to the right. So it would still accelerate to the right. It would still experience a displacement to the right. But the only thing is, there's now only a component of the force which is in the direction of the displacement. The other component of this force, the vertical component, is not moving the object at all because we said the weight is much bigger. And so the vertical component of this force is actually not producing any displacement, and so we say it's not doing any work. So therefore, we now have a force, like we said, which is at an angle. The actual force is at an angle to the displacement. And we are going to now have to work with the component of this force in the direction of this displacement, which I'm going to call Fx. It's the x component. Now you might remember from vectors, cos of this angle, if you drew this force and its component as vectors, cos of this angle would be adjacent over hypotenuse, which would be in this case adjacent is Fx and hypotenuse is the force. It would be Fx over F. Now we can use that to help us because our formula for work done is going to now be the component of the force in the x direction multiplied by the displacement, which makes sense because that's the only bit of the force that's doing any work on the object. The component of the force we've called Fx, and obviously we're saying the vertical component does not move the object. Since cos theta equals Fx over F, we can rearrange that, take the F to this side, and we'll have Fx is equal to F cos theta. Now we can put that into our equation. Since we had Fx delta x, instead of Fx, we can put F cos theta. So we put that F cos theta over here, and we got F cos theta times delta x. Now, if you rearrange that a little bit, you'll end up with this formula. W equals F times delta x cos theta. And that's the formula that the syllabus will give you. And the nice thing about this formula is it covers all the directions of F and delta x. If you change the angle between the force and the displacement, you can still use this formula to work out the amount of work that's done. So let's have a look at a few options. All right, before that, we'll just run through the theory quickly. So the work is the product of the resultant force applied in the direction of motion. That's why we're talking about Fx. And obviously the displacement of the object in that direction. So there's our object, there's the displacement, there's the force, there's the angle, and there's the component of that force in that direction. And then we said the unit of work obviously is the Newton meter, which is the same as the joule. Joule is the amount of force therefore done when 1 Newton acts over 1 meter. So 1 joule equals 1 Newton meter. A couple of other points down here. We've already spoken about calculating the x component of the force. We treat work as a scalar quantity, so we don't state a direction. And then what we have is, we're going to talk about these cases in a bit, but obviously if there's no movement, if delta x is 0, then the formula is going to turn out to be, the work is going to turn out to be 0. And we're going to look at this in a bit more detail as well. If the displacement is perpendicular to the force, there's also going to be no work done. We'll look at those two in a minute. Let's go back through this one. The first one we did where theta was 0, in other words the force and the displacement were in the same direction. The formula still applies because cos of theta would have been cos of 0, and cos of 0 is 1. So your equation would again become F is equal to, W is equal to F times delta x. So it works for all values. Right, let's go and consider